Hello, hello everyone. Uh, Embedded Linux systems. I'm Hariharan, Embedded Linux developer and trainer. Here this session we shall see about overview about embedded Linux systems and environment, the various software components of the embedded Linux that we shall move forward here. Before diving into the embedded Linux, some brief what is embedded system. Embedded system basically that with comparison with the general purpose system, embedded system is designed for dedicated function. For example, a DVD player or digital TV. Even though we can add our digital video card into our computer and we can able to see in our desktop itself, we are going for a separate one, digital television, those things, because of it gives more performance with respect to that specific application. For example, digital TV is dedicated to just capture and display that information. That's why it was very performance with respect to its function basically. But general purpose, it was designed to it supports different actions that we may not expect good performance for that our own specific applications. And the embedded systems developed for lower power consumption and smaller in size, and our smartphones are very smaller. It was designed very small in size, and it should be rugged and operating ranges. And one more thing is something like embedded systems. For example, if you are taking a small motor controller, it has to just actuate that relays with respect to that, whether water controller, water tank controller, taking an example, it just has to enable that relays according to that, whether the water tank is full or not. It does not need to be much more powerful. It's has that limited processing power has over the general purpose. Basically, that is enough for that application. It just has to monitor that water level and it has to actuate that relay. That's enough. It should not be more powerful for like our CPU Core i3, Core i7, those kind of that much powerful is not needed for embedded systems. And that reducing that processing power, you always get that reduced cost. And it has, since we have to use that very little powered one depending upon the application. For example, water tank controller required limited application, PLC required something more, something like temperature controller required something more, the smartphones requires something more, something like it's depends upon that application basically. Since it depends upon the application, it is little complex in programming. We have to be a constrained programming so that our source code will not fit into gigabytes or megabytes. Basically depends upon that. We should make it as sometimes we may need to write a code within less than 1 kilobytes that should get that application up and running, that specific one. And we have different procedures to be used for programming and development that we will see in the later part. But it was not difficult. It's a little complex, but it was not difficult to learn, and mostly based on microcontrollers. Embedded systems are mostly based on microcontrollers because it needs, as we discussed, embedded systems are targeted for specific application. It has to have all those peripherals into that microcontrollers. For example, we have that GPIOs, we have that I2C, we have that SPI, and we have that HDMI display. For example, in case of smartphone, LCD display interface, all those things are present inside the microcontroller itself. That makes that our system to be more good and well and good, so that we can able to work more on the embedded systems. Embedded systems design constraints of the embedded system is something like embedded design should be in such a way that it's reduced in size, make it more compact in nature. That if, for example, when we are building a smartwatch, it should not be like a wall clock. It should be like our watch. That's our thing, that the reduce its size and make it more compact. That means that one. Yeah. And we should not build a product with the embedded system for something like what we can say $1,000, $2,000. We cannot make, for example, a smartwatch. That it should be within that limit. The product cost should be as much as lower that it has to be, but it has to perform reliably. It has to match with the price and performance, so that embedded system will hit the market. Yeah. And we seen about the embedded systems here, and we will see what is embedded Linux. Embedded Linux is, we have that operating systems. For example, for the small thing like water tank controller, we may not require that operating systems. But when we are going for higher applications, something like smartphones, something like digital television, something like smart TVs, all those things requires operating system, so that it can able to do multiple multi-process and multi-actions it can able to do. For that, Linux usage of Linux operating system over the embedded system on embedded system domain is called embedded Linux basically. And basically that embedded Linux is embedded Linux kernel and software components into the embedded system. For example, whatever be the application we are developing, for example, if you are developing like a Wi-Fi wireless access point based on Linux, we should have that some of the components like Linux kernel, and then applications, something like a wireless router kind of application, that has to be components are available that can be integrated into the embedded systems. If you are making a digital television, that kind of a display, something like a YouTube in the smart television, all those things has to be integrated, and it has to be made as a product. That it has a provision to have Linux kernel and its software components into the embedded system. And Linux kernel also ported on non-desktop processor like ARM, MIPS, PowerPC, Microblaze, Blackfin, Coldfire, AVR32. But these are all things not limited. Not more has been ported to the embedded Linux basically. And since this kind of all those things are ported and ready, we can use our Linux operating system to the embedded applications. Since we have that Linux OS running on embedded processor, we can use it obviously that embedded Linux into that embedded systems basically here. And also Linux also became popular due to proprietary OS overcoming that proprietary OS basically. And we can see that advantage of Linux for embedded, it's completely free and open source and very large user community. For example, if you are developing a driver, if you need a driver for one device that may be used in x86, Core i3 or Core i5 or Core i7, that we can able to reuse, and we can easily come up with that our embedded system platform. And we have openly available complete end-to-end software. For example, different kind of softwares that can be integrated, and we can able to build our own application. That is the power of embedded Linux here. and we can easily configure and customize using the tools, something like buildroot, yocto, open embedded. All those things are there that we will see one by one, but it has the complete features to create your own embedded Linux image basically, and easier for the upgrades and expanding that feature. And we have complete set of device driver based on Linux, and which can be easily moved forward to that embedded platform which we are developing. That's called porting, that driver porting, that we can able to we will see that what is driver porting, those things in our next sessions. That, and then it has the complete open source networking and telecommunication software stack. Then it can be ported into Wi-Fi networking terminal or telecommunication terminals. It can be easily ported, and it has that Bluetooth, wireless, and everything. It also it can be easily developed that with the consumer electronics devices as well, that we have that options. And we can see that some devices with embedded Linux, but not limited basically. Here smartphones, Android, Qt, OPE, and we have digital and smart television, smart set-top box, and DVD players, smart DVD players basically, and smart digital watches, and automotive infotainment systems, and enterprises and consumer grade networking switches and routers, shopping kiosk, point of sale terminal, and billing machine, wireless access point, wireless IP cameras, and smart video doorbell, and surveillance camera monitoring. All those things are the some of the application which used embedded Linux, and lot more are there. And we can see over here in normal our desktop, we used to write an application and compile it, and we will generate and we will run over there itself. That is the normal desktop development environment. Comparing to that desktop development environment, we have some small changes, that we will be having separate embedded hardware and development PC. Whatever be the development, we will do it in the development PC, that we shall push into that embedded hardware either through serial port, or either using that Ethernet, or using that JTAG. That if we can use, we will push that application or bootloader or anything, that we will push into that embedded hardware, and we can verify. For that, in order to create an images for a bootloader or anything, we need source code. That it should be like whatever be the embedded hardware, we should have source code based build system, that we should be having in that development PC. And we have that JTAG Debugger, which is used to debug that embedded hardware, and cross compiler basically. Cross compiler is something like a compiler which generates the output that will going to run in another platform. That is the cross compiler. For example, if you are using that ARM based embedded hardware, and development PC is our Core i3 686 based x86 based one, that there is an architecture difference. We are doing the development in x86 and running that our outputs on the ARM platform. Basically, that does by the cross compiler. Cross compiler will run on that x86 platform, and it will generate the output for the ARM platform. That is the cross compiler. And we should have something. We may not have this monitor interface and display to your micro embedded systems, very small and compact, and it has to be those things. For that, we use serial port as our Linux console, so that we can able to run that Linux commands from the serial consoles basically. And in the embedded hardware, we will be running the complete embedded Linux software components, something like a bootloader, Linux, and then root file system, and then application, all those things will be present, and we can see further more in detail. And the development PC components are cross compiler, source code build system, JTAG Debugger, and then serial console. And we can see one by one. Embedded Linux components are bootloader, Linux kernel, root file systems, and applications. Basically, the system boot flow will be, processor will contain a boot ROM which boots a bootloader, and bootloader will load the Linux kernel into the RAM, and then it boots that. Once the Linux kernel booted, it will be given with the kernel arguments which device it has to mount as a root file system, that it will mount that with the root file system. Once the root file system got mounted, it will start installing the start running that services and respective application with respect to that embedded function it was developed. Basically, here we have that platform for running that embedded Linux. We have UDOO Neo platform. UDOO Neo platform is an open source platform, and it has that NXP i.MX6 SoloX application processor, and it has ARM Cortex A9 processor with ARM v7A architecture. It is 1 GB of DDR RAM. Maybe we will go through this again during the cross compiler. Please note that we are using ARM v7A architecture here, and we have 1 GB of DDR3 and a micro HDMI which contains integrated audio and video, and a micro SD card for booting. And you can also make something like half of the partition for booting and half of the partition for data. That's our wish, that we can do as per our requirement. And you can have USB 2.0 host and 2.0 OTG and 10/100 Ethernet for networking, and we have wireless and Bluetooth for Wi-Fi wireless connectivity, and we have Arduino compatible header so that you can plug your Arduino shields and you can start your embedded Linux applications for that, your Arduino shields. That can be done. We can move forward with that one. The cross compiler is the one. It runs on X platform and it generates the output for the Y platform. That is the cross compiler, and GNU compiler collection is ported and created as a cross compiler over here. To install that cross compiler in Ubuntu environment, you can run that sudo apt-get install gcc -4.9 -arm linux GNU EABI HF that we will see over here. Basically, EABI is the one which supports hardware based floating point operations. Something like if you are doing 2 floating points or one floating into another one, it basically not done in the CPU. It will be done by the floating point unit separately, and it gives that output so that it will be faster in floating point operations. And we have HF supports ARM HF architecture, that we have seen that it supports ARM v7 architecture and above. We have ARM v7A. Obviously, HF compiler will supports with that ARM v7 architecture, and results will be good for that specific processor with the ARM v7 and above. But the thing is, we have the options of GCC cross compiler without HF also. But comparing to that, this will be good enough. But the thing is, it cannot be used on lower processor. For example, if you are compiling in with the GNU EABI, you can able to backport and run it on your lower processor one with less than ARM v7 architecture. But if you are building with that GNU EABI HF, you cannot run on the lower platform. It should be good basically. And then we have source code base, and we have different source code bases available. Something like a build root, which is making embedded Linux easier, and Open Embedded Linux build framework, and YAPTO. YAPTO is not an embedded distribution, it helps to create the one basically. And Linux target image builder, this is the NXP Freescale proprietary based image builder. It's deprecated basically, and we are not using with that one. And we have JTAG Debugger, and JTAG Debugger is the one which you can able to access that CPU during that. If, for example, you are getting a board which is nothing running, and then we have to do that, it has to bring up and it has to work. We should have some mechanism to access that CPUs, right? And that will be given by the JTAG Debugger basically. JTAG is the one joint text access group, and which can be used with that open source OpenOCD, which is open on-chip debugger, used to control and access over the processor registers, and we can do that. Basically, this is very useful when you are bringing up a new board, for example DDR initialization, and you can able to verify whether the DDR we can able to write into the DDR, and we can read back the DDR, and system initialization, whatever initialization registers we are doing, that was good and it was accepting, and it can able to move forward, that we can able to see with that JTAG Debugger. And it has used to validate and bring up, for example, when we are making that chips, that boards, we can use that JTAGs to verify that automated scripts whether all the peripherals are running good or not. Then we can use that as a developer tool to debug that systems applications. For example, those things can be done where the program counter got stuck. All those things we can able to see over this, and we have that. This is can be used as a development tool to boot systems, boot up that system registers basically. Basically, this is playing very low level to get that get that configuration of initialization registers basically. And we have a serial console. Serial port works like a console for embedded systems, prints system boot up log messages, acts as a console for both bootloader and Linux kernel. It provides easier way to execute the commands. Linux shell will use that as a console for using setTTY, and in system with LCD display. For example, in your phone it displays that Android screen, for example Android phones, it featured with the Linux, embedded Linux, it displays that icons, all those things. We cannot put our debug messages, right? That's something like kernel is throwing this one, all those things, then that LCD display purpose will gone. Even in that the displays, we will be using serial port for getting that log messages. That we will see how it was there. Here I can show it here. Here we have that serial console Minicom. Minicom is the one user-friendly serial port communication utility. It's text-based serial port, modem control, and terminal emulations. The default settings for UDOO board is baud rate is 115200, and data bits is 8, and parity is none, and stop bits is 1, and then flow control is also none. That we can able to configure this one using here, and we can able to do this here. Maybe I will restart so that we will see about that logs clearly. Yeah, I'm restarting. We are getting that the boot up log messages here. Yes, we are getting, and yeah, it's booting up. The Linux kernel is booting up, and we can able to get that thing, getting the log messages of during the boot up, and also we got the login prompt. We can enter our username and passwords, so that we can able to log in. Here we got the basic prompt, Linux prompt. We can able to do execute ls commands, and maybe we can what else we can do, something like ifconfig to get that informations. Here system got booted, and we can able to execute that Linux commands over here, and maybe we can do that something like a copy. We can do basically here with the copy those things that we can able to do that. Basically, for example, here all those things, copy command, it works. Missing files on arguments, that it can able to do. Now we have seen that something like this, that boot flow over here, that is initially the bootloader will start, and then Linux kernel will start, and then mount application, and then it will be started with that services and applications that we will see over here, how the logs look like, that we will see here. Here we just got started with that bootloader, and it's boot up here till here, and then it loads that Linux kernel images and device tree files, and once that it loads that into the RAM, after loading into the RAM, it's starting the Linux kernel. Then we have started with the Linux kernel from here, and the Linux kernel is started from here, and it does that whatever be the driver components we have added, that it was added over here, and it initialized the serial console, all those things, and then it comes and move forward with this one, and we can see where it mounts, and something like it mounts that VFS, mounted that file system, and then it started with the applications are running, that we can able to see over here. That's it should be here we have got detected our micro SD card, and then we have the systems got that mounted, and once it mounted, it started running that mounted that MMC block 0P2, and then it started running that services, and we got that services and all those things running in background, that we can able to see here. It's bash based shell that we can able to see in details, that one. This is a boot flow that the embedded Linux, it boots from bootloader, and then bootloader loads that Linux kernel from the micro SD card for here. Maybe somewhere it will load that Linux kernel into the RAM, and it starts running the kernel basically, and also it has that extract that Linux kernel and loads that same, and it boots basically. Here some introduction about that UBootloader. UBootloader, universal bootloader, shortly called as U-boot, and it is completely open source and primary bootloader used in embedded devices. It initializes, then boots the Linux kernel. It loads that Linux kernel into the RAM, and then it boots that Linux kernel here. And it also featured with image extraction, so that our Linux kernel image size will get smaller. When we compress here, maybe we can see here how the extraction is happening. Here we have something like a Z image. This is a gzip based image that it has been loaded. Once it is when we are giving, it will extract the kernel image into here, and then it will start loading. Basically that extraction will be taken care by the U-boot, so that kernel image can be compressed, and our embedded devices has limited storage. We cannot put that VM Linux directly, that we have to constrain that compress that Linux image and gzip, and also we have U-boot based compression image formats also, that bzip based compressed image formats also, in which format we need, we have to use that decompression accordingly, and we can able to build boot that Linux kernel accordingly from the U-boot. And here we have feature to provide arguments device tree. For example, here we are providing the Linux kernel arguments is something like this. It has to use the serial port 1, and it has to mount the root with the MMC block 0 P2 partition, and it has to root wait is to wait till it has mounted and the root of a type, and all those things we can able to give it from the bootloader. The Linux will receive that, and it configures that accordingly, so that it boots accordingly over here, and contains first stage and second stage bootloader. For example, we cannot boot that complete block in a single stage. For that, we have two different stages of bootloader, which boots the first stage and second stage, that we will see here. Basically, here we got the print. Here we have the print. This one is for first stage bootloader up to here, and then second stage got loaded from MMC 0, and then it's starting that second stage bootloader here. And it's something like we can make it the first sector that depends upon the boot ROM of the microprocessor. It just loads that first 512 kilobytes of first sector of bytes, and it loads and initializes that DDR RAM. After that, it just boots the loads that second stage bootloader into the RAM and executes the same. Basically, here we have that boot flow. The boot ROM will get started, and first stage bootloader will come up, and then it initializes the memory, and then load that second stage bootloader and start the second stage bootloader over here. Similar way, that based on logs, here we are having initializing the memory, all those things in the first stage bootloader. Basically, boot ROM started this first stage bootloader. Once it is started, it initializes the memory and loads that the second stage bootloader into the RAM here, and then runs that second stage bootloader, which comes up to here, and then it loads that Linux second stage bootloader loads that Linux kernel image basically here, and once it is done, it mounts that root file system and executes basically. Here, Linux kernel is that Unix-like operating systems. It's monolithic. Monolithic means works in kernel space, and Linux kernel will be running in the workspace and alone in supervisor mode. And that means that application will not run in the supervisor mode. Only Linux kernel will run on the supervisor mode, and manages all the hardware peripherals like CPU, memory, IO, and access, all those things. And Linux kernel is running in the supervisor mode. You cannot access that hardware directly by the user application. There should be some way provided by the Linux kernel, so that a user application can access. That means the application cannot crash the Linux kernel directly, and it provides an application interface to access the hardware and manages the flexible multiple user access, and it provides an application interface for parallel hardware access, and integrated kernel module, and then dynamic kernel module, so that some drivers will be loaded by default and some drivers can be inserted during the runtime basically there. And we have that option something like this block diagram. Basic block diagrams will be like a memory management and device drivers and scheduler and task management, and we will be having low level CPU initialization, that the kernel will start up with the low level CPU initialization, and then only slowly one by one it will get loaded. And file systems support something like ext2, ext4, fat, all those things. And then network stack, Bluetooth, wireless, or Bluetooth, IP, TCP, IP, Ethernet, all those things, networking stack will come, and we have device tree configures that board informations to the Linux kernel, gives that the board configuration information, what all the peripherals are available, what all the things, where, how it was connected, all those things will be defined by a device tree over here. And we have that root file system got mounted. Root file system folder structure basically contains necessary binaries and libraries to run that Linux basically, and rest of the file system get mounted on top of it. For example, when you are connecting another pen drive or anything, another pen drive to the system, it will be get mounted on top of the root file system. For example, here we got mounted with the root file system. Yeah, here we got mounted with the root file system. Now we have media, UDOO, and then Ubuntu. I connected that pen drive which contains Ubuntu. It got mounted on top of it basically here, and we have different file system can be used, basically ext2, ext4 and ext3 extended file system format, and init.rd initial RAM disk file system loaded into the memory, and we have CramFS compressed ROM file systems, and YAFS for yet another flash file systems, and JFFS2 for journaling flash file systems. And nowadays we are mostly using that ext2 or ext3 or ext4 based file system, since our storage is bigger and it should be used ruggedly. That earlier ext2 was not much stabilized, only for the desktop processor. That time we used YAFS, CramFS and JFFS2 kind of file system. Now we are more into that ext extended file systems. We are more into it. It should be that root file system should be small in general, small in nature, and with the very needed files, so that we will not get into the bigger kind of image storage required for the binaries. For example, Android phone. Whenever you are buying an Android phone, 16 GB phone, almost 3-4 GB gone for the system files. If you are making more memory with the unwanted things, then our complete 16 GB will be gone. We just need depend on the external storage only. For that, we should make that our root file system small in nature. And the root file system structure is something like a bin, so that we can able to see here that it will be very similar to the Linux kernel. Bin, all those things we can able to see. Bin is the one commands, very essential commands for the system boot up, and sbin commands like ifconfig, not intended for the users. Admin have the privilege to access. etc is system specific configuration files. Root is the one home directory for the root user, and lib contains standard shared libraries needed by the application, like C libraries, C++ libraries, GCC libraries, all those things. Lib modules contains loadable kernel modules. Dev/dev is the one which contains special device file systems files, which helps to interface with the device drivers. And temp is the one temporary file storage directory, which will be accessed by all the users, but that file which file opened by the user, that cannot be accessed by another one. But the thing is, this folder is completely accessible by all the users basically. And boot will have that bootstrap files like bootloader, kernel image, initial RAM disk, all those things. MNT is the one temporary mount point, especially for the system admin to use. They will mount and they will just remove those things. And /user will have that user installed applications, binaries, all those things, libraries will be present inside this folder. And proc is the one which contains processor, memory, process, device specific information, system specific information. All those things will be present inside the proc folder. For example, proc devices, proc main info, all those things will be inside the proc folder basically. Here next we can see about that application is basic application will be for embedded Linux is Linux shell provides an interface to Linux system, receives an input and executes the program and displays the output. For example, here we are running our command ls, which receives that input and executes and displays that what are the files available, it displays over here. And we have that something, it allows run binaries, commands, programs and scripts. Also we call it as a Linux command prompt and denoted with the symbols $. Here we can able to see here the $ is present here. And we have that different shells option: Bourne shell, corn shell, born again shell and POSIX shell. Normal usage or born shell or born again shells. Here we will see what is the shell we have used. Here we can see PS. You can see whatever the shell used is a born again shell over here, and the applications packages are depends upon our system needs basically. That we will explore different kind of application for different kind of frameworks for different kind of functions that we will explore further. And that's it. We have hope this will be a good starting for the embedded Linux. If you have any clarification, you can contact me at nvhariharan@nivitech.com. Thank you for watching. Subscribe for more updates. Thanks. Have a nice day.